Today, we are turning our focus to a topic that, while not directly a part of physical chemistry, plays an indispensable role in it: physical quantities and units. This subject may seem somewhat removed from the central themes of physical chemistry, but it holds significant practical relevance to our studies. Why is this topic so crucial? Well, a considerable number of errors that students make in our practical exercises can actually be traced back to incorrect handling of units. These errors can be easily avoided with a robust understanding of physical quantities and their corresponding units. For this reason, we have dedicated this module to this basic concept, which will serve you as a practical tool during your studies in physical chemistry. Feel free to use this module as a reference in the future. And now, let's get started. Let's start with the concept of physical quantity. A physical quantity is a property of a state or process that can be quantitatively determined in a physical object or system. For comparison, we require a common property or characteristic that both entities possess. Consider two lines, for example. Both lines share a common property, length, which we can compare quantitatively. A property is classified as a physical quantity if it holds a numerical value and the ratio between two values of the same property is a real number. This allows comparisons based on a physical quantity to be quantifiable. To determine the numerical ratio, we carry out a comparison process known as a measurement. This process must be unambiguous and reproducible to ensure accuracy. The ability to measure a property is equivalent to defining a physical quantity. Returning to our example with the two lines, we can assess how many times the smaller line fits into the larger line. Let's say the larger line is approximately 3.5 times longer than the smaller one. This comparison constitutes a measurement. All characteristics of an object fall into two categories: physical quantities and all others. Physical sciences focus exclusively on physical quantities. Now, let's continue with the concept of a unit. To determine the value of a measurable property, that means a physical quantity, it is useful to compare it to a well-defined reference quantity of the same kind. This comparative value is what we call a unit of measurements, or simply a unit. The value of a physical quantity can then be expressed as the product of the measured ratio, which is the numerical value, and the unit. The numerical value is typically a non-negative real number. Depending on the definition of the physical quantity, the numerical value can also be any real number or even a complex or an integer number. The definition of a unit is a rather arbitrary convention. It is chosen for convenience or utility. And now, a very crucial point to remember. The numerical value that we get during a measurement depends on the chosen unit. The value of a specific physical quantity is an intrinsic natural property of an object or a system. However, the unit and the numerical value are not natural properties, but tools that we use to describe the value of a physical quantity. So, to correctly describe the value of the physical quantity, the numerical value must match the unit. If a mistake is made and, for instance, one uses a numerical value with a unit that is 10 times larger than the unit originally used to determine that numerical value, the value of the physical quantity doesn't become 10 times larger. In this situation, the description of the value of the physical quantity is simply incorrect. For example, we can choose a specific object that embodies the property of interest. The quantity of this property that the object possesses serves as the reference quantity. To illustrate this concept, let's consider a historical example. In Bern's Zittglogge Tower, you will find measures of lengths that have been publicly displayed since the 17th century. These measures serve as a reference units for lengths. They represent units based on an object. Another approach is to use as a unit of a given physical quantity a value calculated from units of other physical quantities. This approach requires a known physical relationship of the considered physical quantity with other physical quantities. Another possibility is to use the value of a natural physical constant as a unit. This is only possible if a suitable physical constant exists for the desired physical quantity. For example, the elementary charge is used as a unit of electric charge in some systems of natural units. To systematically classify physical quantities, they are organized into a system of quantities. At its core, a system of quantities defines base quantities. The set of base quantities has a property that no base quantity can be expressed in terms of the other base quantities. These base quantities serve as the fundamental building blocks from which we define other quantities in the system. You can compare base quantities of a system of quantities to the axes of Cartesian system of coordinates. The axes are mutually orthogonal, which means that a position of a certain point with respect to one axis cannot be expressed through the positions of this point with respect to other axes. Further kind of quantities that are called derived quantities can be calculated from the base quantities. In fact, all quantities that are included in a system of quantities are derived from the base quantities according to agreed upon rules. That's why it is a system. While various systems of quantities are in principle possible, we will deal exclusively with the International System of Quantities, or ISQ. This system underlies the International System of Units and therefore is a modern international standard in science and technology. The ISQ defines 7 base quantities: length, mass, time, electric current, thermodynamic temperature, amount of substance, and luminous intensity. The International System of Units, or SI, is a modern globally accepted standard system of units. It provides a consistent and universally agreed upon framework to express the results of measurements. This is incredibly important in ensuring that everyone is speaking the same language when it comes to measurements. The SI defines 7 base units, which correspond to the 7 base quantities defined in the International System of Quantities. Since 2019, all base units of SI are defined by assigning exact values to certain physical constants. The specific definition of base units of SI are not crucial for their practical use, but if you are interested, in the science behind these standards, you can read more about it, for example, on Wikipedia. Using 7 base units of SI, it is possible to construct a derived C unit for any derived quantity of the International System of Quantities. And here is the table that summarizes the key information about base quantities of ISQ and the corresponding base units of SI. I hope you find it useful for future reference. The first column shows the base quantities, time, length, mass, and so on. The second column indicates the symbols commonly used to denote these quantities. The third column represents the symbol of dimensions. I will come later to this topic. Finally, these are the basic units. The dimension of a physical quantity is its very general representation within a system of quantities. The numerical values and even units are not relevant here. The dimensions of a physical quantity simply shows how one has to combine base quantities to obtain a physical quantity of this type. We will again deal exclusively with the International System of Quantities. In this system, there are 7 base quantities that also form the basis of the dimensional representation of physical quantities. The symbol of a base quantity that is used to indicate it in the dimensional representation is shown in the previous slide. The analysis of dimensions is a powerful tool that you can use to understand and analyze physical equations. And now let's look at an example. Velocity v is a physical quantity that shows what distance L was traveled by a certain object over a certain time t. Here, it doesn't matter how large the distance is or which units we use to measure this distance, or if we measure it at all. What's important is that we consider some kind of distance, or, referring more specifically to ISQ, something of the same type of physical quantity as length. It's the same with time. We refer to some kind of time. Then, something that is some kind of velocity is always some kind of length divided by some kind of time. Now we express it in a more formal way. The dimension of v is equal to length divided by time, and we write it as capital L times capital T in the power of -1. It also means that a physical quantity of a different dimension, that is, one that is a different combination of base quantities, just cannot be velocity. In general, the dimension of any derived physical quantity can be expressed as a combination of 7 base quantities: time, length, mass, electric current, thermodynamic temperature, amount of substance, luminous intensity, with certain dimensional exponents. Any exponent could be 0, which means that the corresponding base quantity is not used to define the derived physical quantity. In this case, the symbol of the base quantity is usually omitted. If all exponents are equal to 0, we have a dimension of 1. A physical quantity of this type is called a dimensionless quantity. The ratio of two quantities of the same dimension has a dimension of 1 and is a dimensionless quantity. And here are some examples of quantities that are frequently used in physical chemistry. Energy, denoted here as E, has a dimension of time in the power of -2, length in the power of 2, and mass in the power of 1. Pressure, denoted as P, has a dimension of time in the power of -2, length in the power of -1, and mass in the power of 1. Volume, denoted as V, has a dimension of length in the power of 3. And if you look carefully, you will notice that the product of pressure by volume has a dimension of energy. As I have mentioned before, The analysis of dimensions of physical quantities, dimensional analysis, can help you to understand and analyze physical equations. There are a couple of important principles in dimensional analysis that I would like to stress. First, one can never compare, equate, add or subtract quantities that have different dimensions. Doing so would be like comparing apples and oranges, as the saying goes. It is possible to multiply and divide quantities of different dimensions. This process is, in fact, how we construct derived quantities. Secondly, both sides of any physically meaningful equation or inequality must have the same dimensions. This principle is referred to as dimensional homogeneity and is a critical aspect of dimensional analysis. It can be used to perform a quick sanity check on an equation or computational result, allowing us to verify that it at least makes sense dimensionally. I must also warn you that when two physical quantities have the same dimensions, it doesn't always mean that they are comparable or can be added together. They can be two fundamentally different physical quantities that just happen to be of the same dimension. And now we are arriving at the topic of SI units. In contrast to dimensions, the purpose of units is to express the values of physical quantities quantitatively. Analogous to the dimensions of derived quantities, any unit can be expressed as a product of powers of the base units: the second, meter, kilogram, ampere, Kelvin, mole, and candela. Here, the square brackets around the symbol of the quantity Q denote the unit of Q. However, this time we introduce an additional numeric factor denoted as K. When K equals 1, we are dealing with a coherent unit for a derived quantity. A straightforward one-to-one relationship exists between the dimension of a physical quantity and its coherent unit in the international system of units. Each physical quantity has a uniquely defined dimension and correspondingly exactly one coherent SI unit. Any physical quantity Q can be constructed from base quantities using a unique set of dimensional exponents A, B, C, D, E, F, G. Consequently, the coherent unit for the quantity Q is constructed from the base units of SI using the same set of dimensional exponents. Despite all coherent SI units being representable as combinations of base units, SI assigns special names and symbols to 22 derived units, such as Newton, Joule, among others. Once again, here is the general formula for any unit of a derived physical quantity with K equal to 1 representing a coherent SI unit. Coherent SI units are strictly defined and can be used universally. However, they are not always convenient for expressing the results of measurements or calculations when the numerical value is significantly large or small. For convenience, SI provides 24 prefixes that can be used to generate additional non-coherent SI units. These include prefixes like kilo, mega, milli, and micro, among others. These non-coherent SI units are decimal multiples or submultiples of the corresponding coherent SI unit. This can be expressed as K being equal to 10 to the power of n, where n is a non-zero integer. This means n can be 1, minus 1, 2, minus 2, and so on. For 24 specific values of n, which correspond to 24 integer powers of 10, there are these special SI suffixes that represent certain values of the numerical factor k. For example, Kilo corresponds to 10 to the power of 3 or 1,000th. Milli corresponds to 10 to the power of minus 3 or 1,000th, and so forth. It is important to note that due to historical reasons, the base unit of mass in SI is kilogram, which may seem like a non-coherent SI unit. Consequently, the scale of non-coherent SI units of mass is shifted by 3 decimal orders of magnitudes. 1 gram is 10 to the power of minus 3 or 1,000th of a kilogram, technically a millikilogram. 1 milligram is 10 to the power of minus 6 kilograms or a microkilogram, and so on. Finally, all other units that aren't part of the International System of Units are categorized as non-SI units. Many of them are used mostly due to historical reasons. In formal reporting, conversion to SI units is typically expected. As we conclude this module, we will review our key learnings and leave you with some essential practical tips. Remember, each physical quantity possesses a dimension, unless, of course, it is dimensionless. Each value of a physical quantity not only has a numerical value, but also a corresponding unit, unless it is by nature unitless. Don't forget, even natural constants have an appropriate dimension and a corresponding unit. And here are some essential tips that will help you to avoid mistakes in physical calculations. Before calculations, convert all data into values that use coherent SI units. Be sure to include units in your calculations. They are as important as numeric values. Do not disregard and do not overlook them. Check the consistency of dimensions across all expressions and the consistency of all units in your calculations. Any inconsistency in dimensions or units is a clear sign of an error. Having completed this module, you now have a robust foundational understanding of physical quantities and their units. Make sure to continue practicing and improving your skills in performing accurate physical calculations. This skill will be a valuable asset in your future studies and future professional undertakings.